am Ajay Kumar, Assistant Professor, Department of Computer Science and Informatics, Central University of Himachal Pradesh. Today we will study about the exponent evaluation. So, first we have to know what is the meaning of exponent. Okay. So, exponent that is this is the content, that is a to the power n, but before moving ahead we have to know the exponent. What is the meaning of exponent? So, an exponent represents the number of times a number is multiplied by itself. Okay. When 5 is multiplied by itself n number of times, you can write it as 5 into 5 into 5, that is n times, and this is equal to 5 to the power n. So, the above expression 5 to the power n is written as 5 multiplied by itself n times. As a result, the exponent are also known as the power or indices. You can say the 5 to the power n or 5 indices n. So, these are the number which multiply itself, and the number of times, how many number of times is known as the power or indices. Like that is, if I say 3 into 3 into 3 up to 4 times, that is 3 to the power 4. So, here 4 is the indices, okay, that is you can say exponent also. 4 into 4 into 4, that is 4 to the power 3, here 3 is indices or exponent. So, in general meaning of exponent is when a number is multiplied by itself, and if the number how many times will be there, that number, the number of times is known as the exponent or power or indices. So, one very big confusion generally student have, how is the repeated multiplication of the same number different from the repeated addition of the same number. Okay. So, this is very basic thing, but you have to remember it. So, repeated addition is the process of combining equal group of numbers. Multiplication is another term for it. When the same number is repeated, and we can write it as multiplication, like if I say 2 plus 2 plus 2 up to like 5 times. So, we can write it as 5 into 2, that is 10. However, the repeated multiplication of 2 is 2 into 2 into 2, that is 2 to the power 5, and that value will be 32, that is 2 to the power 5. So, where 2 is the base and 5 is the exponent. The exponent 5 indicates that the 2 has been multiplied by itself 5 times. Okay. So, this is the repeated multiplication, and in the last example, this is the repeated addition. So, repeated addition, after repeated addition it will converted into the multiplication, but after after multiplication when a number is multiplied by itself, it will convert it into the indices or exponent. Okay. This is very clear. So, next is how to evaluate the exponent. In generally in Horner's rule, we already discussed when p x equal to a n x to the power n, a n minus 1 x to the power n dot dot a n x n plus a 0 x n. So, if we calculate x to the power n, or at point x equal to a, that is a to the power n, it will take like in general it will take log n in linear time, but somehow if we manage up to log n time also. Okay. So, but computing x to the power n at some point x equal to n, that is a to the power n, tends to brute force multiplication by itself n times. Okay. So, it has many applications in various field. For example, one of the well known field of cryptography or encryption method, that is when we pass any information through network, first we have to encrypt that message and pass through the network and decrypt it another side. So, if a message have bits like in 10 bits or 20 bits, so how it can be encrypted, and on other side how it is decrypted, we have to use that exponent evaluation method. Okay. So, there are two ways we can evaluate that exponent. Okay. Either we can use the left to right binary exponentiation or right to left binary exponentiation. Okay. Actually, we already discussed in Horner's rule, generally a to the power n, if we in naive approach, if we multiply 2 to the power 5, we multiply 2 into 2 up to 5 times. If the value of a is like 100,000 and to the power like 1 million, or that will take lots of time. Okay. So, in this case, in that big number, in case of that big number, we have to use like this binary exponentiation methods, because if we multiply 100,000 to the power like 1 million or 1 crore, that will be the that resultant value will be the out of the integer range. So, that will create the problem. So, in this case we have to use like binary exponential method, and this exponential method will be of two type, left to right binary exponentiation and right to left binary exponentiation. So, first we have to first I am going to discuss left to right binary exponentiation. Okay. In this method, exponent n is represented in binary string, okay, and this will be processed from left to right for exponent computation x to the power n at x equal to a, that is a to the power n. Okay. So, that n will be converted into the binary string. So, what will be the pseudo code? So, pseudo code to compute a to the power n by left to right binary exponentiation method. First, I am using the left to right binary exponentiation method. An array A of size s, okay, with binary string equal to exponent n, where s is the length of binary string n. Okay. If I say n equal to any number, that will converted into the binary, and the binary digit, number of digit, that will be the size s. Okay. There are 6 steps where set pseudo code to compute a to the power n by left to right binary exponentiation method. Set result equal to a and set I equal to s minus 2. S is the size of the exponent which are converted into the binary form, okay, binary digits, number of digits in binary form. So, compute set I equal to s minus 2, we have to calculate s minus 2, and we are calculating left to right binary exponentiation, okay, and I equal to s minus 2, and result will be result into result. Okay. If somehow if we encountered I equal to 1, then compute result equal to result into a, and I equal to I minus minus 1, I equal to I minus minus I minus 1, and if I is less than equal to 0, okay, then go to step 4, that will be the result equal to result into a, and result and finally return computed value as desired or as result. Okay. So, we can see one example also. Input is a to the power n and binary string of length s for exponent n as an array a s. Okay. So, how to calculate compute a to the power n by left to right binary exponentiation method. So, the value will be a to the power n, okay, final resultant value. So, first we have assign the value of a, that is base to result, okay, and you have to start for loop or any while loop or for loop, and assign that initial value of I equal to s minus 2. What is s? S is the number of digits present in the binary value of n, okay, and that is exponent. Okay. When we convert that exponent into the binary form, and that the number of bits available in that binary form is known as, that is s. So, we have to start from s minus 2 to 0, and the result equal to result into result. If we somehow encounter, because this for loop will decrement from s minus 2 to 0, and somehow if we during the calculation, during the iteration, if we encounter a I equal to 1, then the result equal to result into a, and finally after completion of for loop, we get the result, that is a to the power n, that we can calculate through the one example also. So, in this if I want to calculate a to the power 17, okay. So, in this exponent n equal to 17, which is equivalent to binary string 10001, okay. So, what is the length of this binary string? 5, okay. So, a step by step illustration I am showing here. So, the left to right binary exponentiation algorithm for a to the power 7, here s is the length of the string, that is 5. So, iteration 1, from where we have to start? We have to start I equal to s minus 2. So, s value equal to 5. So, 5 minus 2, that is I value equal to 3. So, initial first iteration will be I value equal to 3 and the result will be result into result, and initial result value will be a means that is base. Okay. So, base equal to a, so result equal to result into result, that is a into a, that is a square, and after that you have to check a I equal to 1, a I means a 3 because I have started from I equal to 3. So, is a 3 equal to 1. So, here if 1 triple 0 and 1. So, indices start from 0, 1, 2, 3, 4. Okay. So, a 3 means 0. So, a 3 is not 1. Okay. Then next iteration I minus minus, when we decrement the I value equal to 2, again result will be result into result. So, what will be the value of result in a square? So, result will be a square into a square, that is a to the power 4. Again check the value of a I, that is a 2. So, in string a, the a 2 value will be 0 because a 3 value a 4 value equal to 1, a 3 value equal to 0, a 2 value equal to 0, that is not equal to 1. Again the decrement the value of I, that is I equal to 1, and result equal to result into result, that is a to the power 4 into a to the power 4, that is by mistake it is written a to the power 4, but it will be the a to the power 8. And if we check the value of a 1, that is also a 0, that is not 1. Again check decrement the value of I, that I value will be 0, and the result will be a to the power, that is result equal to result into result, that is 8 into a to the power 8 into a to the power 8, that is a to the power 16. And if we check a 0 that is 1. So, if the value of a 0 equal to 1, then result equal to result into a. So, result equal to a to the power 16 and a to the power 16 into a, that is a to the power 17, and finally return a to the power 17. So, in this example, how many multiplication is there? 1 in iteration 1, 1 multiplication, iteration 2, 1 multiplication, iteration 3, 1 multiplication. So, total 4, and in iteration 4 there are 2 multiplications. So, total 5 multiplication are there, instead of if we multiply a to the power 17. So, how many times you have to multiply? You have to multiply the 16 multiplication. So, in case of 16 multiplication, we multiply only 5. So, you can see in brute force it will take n minus 1, and in this case it will take like log n, in terms of log n when we calculate further. So, in simply for a to the power 17, in left to right binary exponentiation if we use, then we only have to perform 5 multiplication operation, but if we use the brute force or naive approach, we have to use 16 multiplication. So, here you can see we can compare the time complexity. So, the complexity analysis, this algorithm perform either 1 multiplication or 2 multiplication in each iteration for a for loop in line number 2 of the algorithm. So, total number of multiplication in the algorithm for computing and will be in the range of s minus 1 to 2s minus 1, where s is the number of binary string equivalent to exponent n, and f is the function that represent number of multiplication in terms of exponent n. So, complexity of the algorithm will be log of n base 2, as n can be represented in binary by using maximum of s bit, that is n equal to 2 to the power s. Okay. That means either it will be value 0 or 1. So, n equal to 2 to the power s. So, s equal to order of log n. Okay. So, this is very useful, because in general we have to perform like how many iteration will be there, order of n, but if we use left to right binary exponentiation, the time complexity is log of n. So, n and log of n, you can compare the graph of n and log n, you can see the how much time you have reduced, and in this way we can use this method where the time complexity is log n base 2. So, next approach is right to left binary exponentiation. We already studied left to right binary exponentiation. Here right to left binary exponentiation. In right to left binary exponentiation, to compute a to the power n, processing of bits will start from least significant bit to the most significant bit. That means, if I say that is 1 the binary value of 17 equal to 10001, least significant bit is from left bit, that is 1, and right significant bit 1. So, here the we have to start from the least significant bit to most significant, means we have to start from the right to left. Okay. So, input is a to the power n and binary string of length s for exponent n as an array a s. So, output value will be the final value of a to the power n. Okay. So, in this case algorithm is almost similar, but there will be some changes. First we have to assign the base value, that is a to x. If a 0 equal to 1, then result equal to a simply, okay. Else result equal to 1. Next, for I equal to 1 to s minus 1, x equal to x into x. If a I equal to 1, result equal to result into x. So, and finally return result, that is a to the power n. So, here if we want to compute a to the power 17 with using this algorithm, how to use this algorithm in the case of a to the power 17. So, in this exponent n equal to 17, which is equivalent to binary string 10001, that is s equal to 5, since a 0 equal to 1, okay, a 0 equal to 1 means a rightmost bit, that is the least significant bit, that value will be 1. So, in this case result equal to a, because if a 0 equal to 1, then result equal to 1, and this, that is the line number 2 and 3. With the help of line number 2 and 3, result value will be a. Okay. And if we increase the value of I, that is I equal to 1. So, if I equal to 1, that is in that case, because for loop, if we use the for loop I equal to 1 to s minus 1, that is line number 6. So, what will be the value of x? X equal to x into x. So, here the x value will be a into a, because here already x equal to a at line number 1. So, x value will be a into a, that is a square, and we have to check. What we have to check? We have to check either a I equal to 1 or not. So, here a 1 because I value equal to 1. So, a 1 equal to a 1 equal to 0, that is not equal to 1. So, again move the next iteration I equal to 2. When I equal to 2, x equal to what is the x, that is in x equal to x into x. So, x equal to what is the value of x, that is a square. So, a square into a square, that is a to the power 4, and again we have to check the a I, that is a 2, that is equal to 0, not equal to 1. Again update the value of I, that is I equal to 3, and that value x equal to a to the power 4 into a to the power 4, that is a to the power 8, and again you have to check the value of a 3, that a 3 is not equal to 1, because a 3 is 0. So, again you have to update the value of I, that is I equal to 4, and x value equal to x into x, that is a to the power 8 into a to the power 8, that is a to the power 16, and you have to check the ai means a4 value is 1, because least significant to most significant bit is also 1. So, in this case using this algorithm, if a I equal to 1, result equal to result into x. So, what is the value of earlier value of result equal to a? So, here result equal to result into x. So, result value earlier value result equal to a, and x value in previous step, that is iteration 4, that value is a to the power 16. So, a into a to the power 16, that is a to the power 17. So, finally, return a to the power 17. So, in analysis of this complexity, how to analyze this complexity? In this example, total number of multiplication is 5, again with the same. In iteration 1, the number of multiplication is 1, iteration 2, number of multiplication is 1, iteration 3, 1, iteration 4, number of multiplication is how many multiplication? 2 multiplication. So, total number of multiplication is 5, instead of 16 multiplication in brute force algorithm. Earlier in like lemon approach, if we multiply, if we want to calculate a to the power 17, we have to multiply 16 times, okay, that is n minus 1. So, this algorithm perform either one multiplication or two multiplication in each iteration of for loop as shown in line number 6. So, complexity of the algorithm will be log n base 2. Okay. Again in left exponentiation or right exponentiation, the algorithm will give the same complexity order of log n base 2, because at each step almost you have to divide the problem size by 2. So, as n can be representation in binary by using maximum of s bit, because the when we convert that exponent n in the binary form, that is in the form of 0 and 1, either we can take that number of multiplication will depend upon the value of bits. If the value of bits is 1, the 2 application will happen. If value of bits equal to 0, that is 1 application will happen. So, n equal to 2 to the power s, which further s equal to order of log n base 2. So, overall if we multiply in any exponent evaluation, we generally multiply the same number again and again. If we have a power of a to the power n, we have to multiply a into up to n times, that is we have to perform n minus 1 multiplication. In that case, the total time complexity will be order of n. Okay. But if we use that left exponentiation or right exponentiation, left to right exponentiation or right to left exponentiation, that time complexity will be reduced from big O of n to big O of log of n. That is very, very important, because if we use in is the polynomial this exponent evaluation approach in cryptography or network analysis, that approach will take lot of time, because the power will be very high, too much. So, in this case we have to convert that power into the binary form, and in that binary form we can use either left to right exponentiation method or right to left exponentiation method. With the help of that exponentiation method, we can get the time complexity order of log n. So, order of using order of log n, because at each step we reduce the problem size by 2. So, with the help, because in Lemon approach we use total like n minus 1 multiplication, and in this approach we use log n approach. So, thank you. We can use this method for the cryptography or for like another network analysis problems. So, thank you so much.